particles, right?
Yeah, and it's a pretty good name, actually.
Because they're just unbelievably small, almost no mass, and crucially, no electric charge.
Which means they hardly interact with, well,
Well,
anything.
exactly. Like trillions of them are zipping through you, through the planet, constantly.
And almost none of them hit anything. They just keep going.
So the big challenge, the one that's fascinating here, is how on earth do you detect something like that? Something so determined not to be detected.
It's a massive technological puzzle.
Hmm.
You're basically building this giant net for things that almost always slip through the holes.
Right. And this deep dive we're doing, looking at your source material on dense materials for neutrino detection, seems to zero in on one core idea.
Which is?
Maybe it's about just sheer numbers, packing more stuff into the detector, using the absolute densest materials we can find, or maybe even imagine.
That's the core concept, yeah. So our mission today, based on that material you shared, is to really dig into why density might be a solution here. And look at what materials are actually being considered, some super rare things we have on Earth, and some pretty wild theoretical ideas.
Stuff that sounds almost sci-fi.
Definitely leans that way. And importantly, we need to talk about the real-world hurdles. What makes this so hard to actually do?
Okay, let's dive in then. So first things first, the basic physics. Why does making a detector denser actually help catch these things?
Well, it boils down to how neutrinos interact. They use the weak nuclear force.
Okay.
And the probability of any single neutrino hitting any single particle in your detector, that's what physicists call the interaction cross-section. It's just incredibly tiny, fundamentally small.
Right, and that's the part we can't really change, the basic interaction probability itself.
Exactly. But the total number of interactions you might actually see over time in your detector, that depends on more than just that tiny probability.
Ah, okay. What else?
It's like a three-part equation. There's the neutrino flux, basically how many neutrinos are actually flying through your detector's area.
Makes sense.
Then there's that tiny interaction cross-section we talked about.
The really small number.
Yep. And the third piece, the crucial one for this discussion, is the total number of target particles you've managed to cram into your detector's active volume.
Ah, okay, there it is. So density directly boosts that third factor, the number of targets.
Precisely. I mean, think about it simply. Denser stuff just has more protons, neutrons, electrons. The particles a neutrino could bump into packed into the same amount of space.
Like comparing a box of feathers to a box of lead bricks, same size box.
Exactly. So if your detector is, say, 1 cubic meter, and it's made of something super dense, it just contains vastly more potential targets than if it were made of something light, like water or even plastic scintillator.
Okay, so you're not making the interaction itself more likely, you're just putting vastly more potential things in the neutrino's path within your detector volume.
That's a great way to put it. You increase the odds simply by having more targets available in the space you're watching.
So based on the materials you were looking at, what are the real-world heavyweights, the densest things we actually know exist naturally?
Well, the sources highlight two main contenders, osmium and iridium.
Osmium and iridium. How dense are we talking?
Osmium is around 22.59 grams per cubic centimeter. Iridium's just a tiny bit less, like 22.56.
Whoa. That's really dense. You mentioned lead before. That's only about half that, right? Around 11-ish?
Yeah, lead's about 11.34 GC meter, and water, for comparison, is just 1. So these are incredibly packed materials.
So the big advantage is just stuffing loads of nuclei into a small space.
That's the main draw, yes. Especially for certain types of interactions with low-energy neutrinos. Think neutrinos from nuclear reactors or from supernovae.
Right.
For those, there's a specific process called coherent elastic neutrino-nucleus scattering, or CNS for short.
CNS.
Right.
CNS. Okay. What's special about that?
In CNS, the neutrino doesn't just hit one proton or neutron. It sort of interacts with the entire nucleus all at once.
Like a gentle nudge to the whole thing.
Kind of, yeah. And the important bit is that the probability, the cross-section for CNS, goes up with the square of the number of neutrons in the nucleus.
Ah, the square. So heavy elements with tons of neutrons are way better targets.
Exactly. Osmium and iridium, being super heavy, have lots of neutrons, making them theoretically ideal for seeing CNS interactions.
And if you can get more interactions in a smaller space, does that mean maybe smaller detectors?
That's a potential benefit, yes. If you need a certain number of target nuclei to get a decent event rate, you can achieve that goal with a much more compact detector if the material itself is super dense.
Which could be useful in places where you don't have, like, a giant underground cavern.
Right. maybe for monitoring nuclear reactors up close, perhaps for non-proliferation or for certain fundamental physics experiments that need to be near the neutrino source.
Oh, osmium and iridium. I mean, those sound like they'd be incredibly expensive and rare.
Oh, absolutely. That's where the huge practical challenges come in. Cost and just plain availability are major roadblocks. These are precious metals. They're rare, hard to work with, and extremely costly. Building a neutrino detector, which often needs to be massive to see anything out of pure osmium. Forget about it, economically speaking, with today's tech.
Right. You need huge volumes usually. So cost is killer. What else?
Signal detection itself is really tricky with CNS. That nudge the nucleus gets, it results in a tiny amount of recoil energy.
So it's hard to even see that it happened.
Extremely hard. You need detectors with incredibly low energy thresholds, super sensitive, and then there's background radiation.
The constant enemy of neutrino experiments.
Always. These heavy materials, or impurities mixed in with them, can have naturally radioactive isotopes. And the decays from those can easily create signals that look just like the faint neutrino interaction you're hunting for, or just drown it out completely.
Okay, so osmium and iridium, theoretically cool for CNS, compact detectors, but practically very, very tough.
That sums it up pretty well.
What about something more manageable, like lead? You mentioned it's denser than water, but less than osmium.
Lead is a really important one, yeah. The sources definitely mention it as a practical compromise. It's around 11.34 GC-MeO, so still pretty dense.
But way cheaper and easier to get hold of than osmium.
Vastly cheaper, much more available, and easier to handle safely. And it still has a high atomic number, meaning lots of protons and neutrons packed in compared to lighter stuff. Plus, it's already used everywhere in physics experiments as shielding against unwanted background radiation. It's great at stopping other particles.
Makes sense. Did the sources mention anything else in that sort of very dense but maybe usable category, like tungsten or gold?
They did, briefly, yeah. Tungsten's dense, around 19.3 GC-MeO, and gold is similar, 19.32. So density-wise, they're up there near osmium and iridium.
But probably facing similar issues with cost and scaling up to huge detector sizes?
Pretty much the same story, yes. Great density, but cost, availability, and making truly enormous detectors out of them remain significant challenges.
So thinking about how these materials are actually used, or could be used, your sources detailed some specifics beyond just being dense.
We talked about enhancing CNS detection for low-energy neutrinos. That's a big one. And enabling those more compact detector designs.
Right.
But they also mentioned using them as specific targets in certain kinds of experiments. Radiochemical experiments, for instance.
Radiochemical, like the famous Homestake experiment that first detected solar neutrinos using, wasn't it cleaning fluid?
Yeah, conceptually similar idea. You use a target material where the neutrino interaction changes some atoms into a different, usually radioactive isotope. Then you chemically separate and count those specific atoms.
Okay.
The sources specifically mentioned looking into using iridium in sensors for something called barium tagging. This is relevant for experiments searching for a very rare hypothetical process called neutrinoless double beta decay. The idea is to use the iridium to help identify a specific decay product, barium.
Wow, okay, that's getting really specific into the material science meeting the particle physics needs.
It really is.
Oh.
It shows how tailored the material choices can become.
What about at the other end of the energy scale? High-energy neutrino experiments.
There, dense materials like lead, or sometimes tungsten, are often used in detectors called calorimeters.
Calorimeters.
Yeah.
Like measuring calories, heat, but for particles.
Sort of, yeah. They're designed to completely absorb all the particles produced when a high-energy neutrino does interact and measure their total energy.
And density helps absorb everything.
Exactly. High density means the shower of secondary particles created by the interaction gets contained within a smaller volume. It stops everything quickly, letting you measure the total energy deposited more accurately.
But hang on, doesn't density create another problem? Lots of detectors work by seeing light, right? Like Cherenkov light or scintillation light produced when particles pass through.
That's a huge trade-off. You're absolutely right.
Dense stuff is often opaque.
Very often, yes. Materials like lead or tungsten are not transparent. So while they're great at stopping particles and packing in targets, they can completely block the faint light signals that many detectors rely on to actually see the interaction and reconstruct what happened.
So you gain interaction probability per volume, but you might lose the ability to effectively read out the signal.
Precisely. It's a constant balancing act in detector design. Density versus signal clarity or readout efficiency.
Okay, that covers the known dense stuff. Now, let's shift gears. Your sources mentioned theoretically possible super dense materials. This is where it gets really out there.
Yeah, this is definitely pushing the boundaries, moving towards speculative physics and material science. We're talking about matter even denser than anything on the periodic table under normal conditions.
Okay, like what examples did the material give?
Well, they touched on hypothetical superdense forms of carbon allotropes, denser than diamond, maybe formed under extreme pressure, but that's quite speculative.
Mm-hmm.
The ultimate example, though, the one that really highlights the concept, is nuclear matter, or more specifically, neutron star matter.
Neutron star matter. You mean the actual stuff inside a neutron star?
Exactly that. The remnants of collapsed massive stars. This is, as far as we know, the densest form of stable matter in the universe.
How dense are we talking compared to osmium, which was already mind-blowing?
It's not even close. We're talking densities around 10 to the power of 14 or 10 to the power of 15 grams per cubic centimeter.
10 to the 14? That's 100 trillion times denser than water.
Something like that, yeah. Orders upon orders of magnitude denser than osmium or anything else we handle on Earth.
So the theoretical advantage for neutrino detection would be just absurd.
Completely off the charts. The density is so high that the interaction rate per unit volume would be astronomical. The sources suggest, hypothetically, if you could somehow have a stable thimbleful of this stuff,
Just a thimbleful.
it would contain as many target nuclei as a truly enormous volume of ordinary matter.
Yeah.
It would be an unbelievably efficient neutrino detector, purely in terms of interaction rate for its size.
Wow. Okay. But I feel a giant but coming. The challenges must be equally astronomical.
Oh, absolutely massive. Bringing this back to reality,
Mm-hmm.
the hurdles are, for now, insurmountable.
Like what?
Well, the biggest ones are creation and stability. This kind of matter is only stable because of the immense gravitational pressure inside a neutron star.
You can't just make it in a lab here on Earth.
Nope. We have absolutely no way to create or contain that kind of pressure or matter here. It would just explode, basically, if you took it out of the star.
Okay, so building a detector using actual neutron star matter is firmly science fiction.
Completely. And even if, by some magic, you could stabilize a tiny bit, how would you get a signal out? The conditions inside that matter are so extreme, so exotic, figuring out how to detect a tiny neutrino interaction within it would be another immense challenge. Our usual sensor ideas likely wouldn't work.
But the material mentions some kind of speculative potential, maybe not using it directly.
Right, it's more of a conceptual point.
Mm.
The speculation is, if humanity could ever create any form of stable matter significantly denser than, say, osmium, even if it wasn't neutron star dense, even small amounts could potentially revolutionize detector design. You could drastically shrink the volume needed for a given sensitivity. But again, that's highly theoretical, way off in the future, if ever.
And the sources also pointed out that we do kind of use neutron stars already, just not by building with them.
That's a really important point they made, yeah. We study neutrinos by observing neutron stars and the events that create them, like supernovae.
Ah, so the star itself acts like a natural laboratory.
Exactly. Nature uses its densest material, the neutron star and the processes around it, to generate neutrino signals. We then observe those signals, or the effects they have on the star, using telescopes and other instruments. It's a form of remote sensing, using nature's own superdense object to learn about neutrinos.
Okay, so let's pull all this together. We've talked about rare, dense elements, more common ones like lead, and this theoretical neutron star stuff. Looking across the board, what are the big recurring hurdles when trying to use density to catch neutrinos?
Well, we've hit on most of them, but synthesizing it. For the known dense materials like osmium or iridium, cost and scalability are just huge killers. Making detectors big enough is often prohibitively expensive.
Right, the sheer scale needed.
And then there's signal readout. That's a constant battle.
The opacity problem.
Yeah. Density is great for targets, but the material also has to let you see the signal, the light, or charge, or maybe vibrations, phonons. And many dense materials just aren't transparent enough for common techniques.
Then background radiation. Always there.
Always. It doesn't matter how dense your material is, if it's radioactive itself, or you can't shield it well enough, those background signals can easily overwhelm the faint neutrino signal. So material purity and shielding are critical.
You also mentioned needing really sensitive detectors for things like CENS.
That's key too. Energy threshold and resolution. Boosting the interaction rate with density is only half the story. Your detector still needs to be sensitive enough to actually measure the tiny energy kick from the interaction, especially for those low-energy CENS.
And finally, for the really exotic stuff, like neutron star matter.
Technological feasibility is the ultimate wall right now. We just can't make or stabilize that kind of material on Earth, period.
So, taking a step back from this deep dive into your sources, the takeaway seems to be that using dense materials is definitely a promising idea, something physicists are actively working on.
For sure. It's a clear path to potentially increasing interaction rates, maybe leading to more compact detectors for certain applications.
But it's not a magic bullet, it's all about trade-offs.
Absolutely. It's a complex optimization game. You're constantly balancing the gain you get from density against the cost, the difficulty of getting a clear signal out, controlling background noise, the required energy sensitivity, and just what's actually buildable with current or near-future technology.
And it really shows how scientists are pushing on all fronts, right? Looking at the densest things we know exist, even if they're difficult, and even thinking about these extreme states of matter, like inside neutron stars, all just to try and catch these elusive particles.
Exactly. It's that relentless drive to solve a fundamental detection problem.
Which kind of leaves us with a final thought, maybe something for you, the listener, to mull over.
Yeah, given the big challenges with the dense materials we can get, like cost and signal clarity, and the seeming impossibility of making detectors out of neutron star stuff.
What comes next? What completely new materials, maybe with exotic properties we haven't even thought of, or totally different detection techniques altogether?
Perhaps inspired by these ideas about density or signal extraction. What might emerge down the road? What breakthrough could finally let us capture these ghost particles reliably and on a massive scale? What's cooking in the labs or theoretical calculations right now?